Okay, good afternoon, everybody. Welcome to the third course of the KIOS Graduate Training School. It's my great pleasure to introduce today's speaker, Florian Dörfler, who is a professor of automatic control at ETH Zurich in Switzerland. And let me just say a few things. You have probably already read the bio, but let me just say a few things. He received his comma degree from University of Stuttgart in Germany in 2008, and the PhD degree in mechanical engineering from the University of California at Santa Barbara in 2013. He was from 2013 to 2014, he was an assistant professor at the University of California at Los Angeles at the UCLA. His research interests are centered around automatic control, system theory, and optimization, with particular focus on network systems, data-driven settings, and applications to power systems. Florian is the recipient of several very prestigious young research awards, such as the IFAC Manfred Thomas Medal in 2020, and also the UCA, the European Control Award in 2020. His students were winners or finalists of Best Paper Awards at several the best conferences in the field, such as the European Control Conference, the American Control Conference, the Conference on Decision and Control, the PES General Meeting, and also the PES Power Tech Conference. Florian is also the recipient of some also prestigious Best Paper awards, such as the Hugo Schack Best Paper Award, the Automatica Best Paper Award, the IEEE Transactions on Power Electronics Paper Award, Best Prize Paper Award, and several others, which I'm not going to mention. And he's also currently serving in the European Control Association and also as a senior editor of Automatica. So, and today's talk, it's a very interesting topic that I hope a lot of you would be interested. Florian, it's really our pleasure to have you here. Look forward to your...
Perfect. Thank you very much.
Thank you.
It's the kind introduction. So, welcome everybody. It's a pleasure to be here. After some back and forth with the organizers, we decided on this topic because we thought it nicely brings together elements from control, optimization, data, but also processes and power electronics. Before I jump into it, maybe a quick assessment of the audience. So I just ask you how you affiliate yourself with topics, and you can give me hands up, then maybe I can tune in to the audience. So who would affiliate themselves with being a control engineer? Optimization, power systems, power electronics, power electronics. Sorry. All right, sounds good. So then I'll roughly know. I guess I missed a few people because not everybody raised their hand. But let's see if we can tune into that level. Good. So you don't have to explain this picture or understand this picture yet. But at the end of this lecture, it will be clear what this picture symbolizes and means. Good. Quickly want to acknowledge my collaborators. Main takeaway from that slide is if you want to collaborate with us, you have to be in one way or another a rock climber. Other than when you're more senior, like John Ligaros, then you can also be a diver. But that's what most keeps you together, the sports. So that's been mostly work with a PhD student about one generation ago, Jeremy, who invented all of this. And then it got passed on through many other people in collaborations. But he was the main inventor and driver. Likewise, Ivan Markovsky has been way ahead of the curve. He worked on these topics 50 years ago when nobody else did. And now people are rediscovering all his old papers. Good. I want to kick off the lecture with some high-level thoughts on this entire field of data-driven control, or just data and engineering. So obviously, there's increasing role, importance, hype, and buzz around data-centric methods in all areas of both industry, but also science, engineering generally, due to some reasons. Of course, as a scientist, I'd like to think because we have such cool new methods, like new advanced statistics, optimization, algorithms, and so on. But to be honest, that's not really true. That's what we think. What is the real reason why these methods gets increasingly adopted? The real reason is brute force. Because now we have a lot of computing power, we have plenty of GPUs, we have plenty of data available, lots of storage. And that's the reason why people send in ever more data-driven methods. And of course, everybody wants to have the piece of the cake, so the general frenzy surrounding big data machine learning. So those are the real reasons why these methods get increasingly adopted. And even in very conservative industries, like I work a lot with cloud operators, they would not even look into more advanced controls, but suddenly they ask me, hey, can we use large language models for system operation? So yeah, that's the general frenzy. So everybody has their own opinion on machine learning. Some love it, some hate it, but whatever your opinion is, it's too big to be ignored. So we may just well play with it, and one that is the also relevance of these methods in more classical control problems, respectively, should we solve more classical control problems from that perspective? And I believe the community has somewhat made up its mind. So nowadays, if you go to any major mainstream control conference, at least half the talks will be on some sort of AI methods. And I quote from the 2030 Control Society Roadmap. There's about 100, 150 researchers coming together, all in Stockholm about 3 years ago, to write this big document about where to go in the next 10 years. And one of the opening paragraphs, this one of the major developments in control over the past decade, one of the most important going forward, is the interaction of control and machine learning. That's just a statement, right? So, because we admitted defeat. Let's go there. And so this just not just make the expert journals, but also when you go to the more mainstream journals, suddenly you would see control on the cover of Nature. This is from a colleague of mine, Davide Scaramuzza in Zurich, who essentially runs some sort of combination of MPC and reinforcement learning on his drones. And he wins various competitions, so he can beat the best drone races in the world, and made multiple covers of that. So suddenly control becomes very much in the limelight, which of course we appreciate. But also in the more expert journals, maybe some of you that are affiliated with control have seen these type of magazines, the Close magazine that you got on your inbox. And we have just 2 special issues in data-driven. It becomes more and more relevant. So those are the high-level thoughts. Let me zoom in a little bit. There's, in general, you can say 2 philosophically big approaches to what you can do with a black box. Let it be in control or more general optimization-based context. It's the following. One pipeline is called indirect. The other one is called direct. Indirect is the more classical approach. So you're confronted with a black box and you want to do some decision making. Let it either be forward optimization or feedback control. The indirect approach goes through a model. So you take your data. From the data, you identify a model. That's called systematification. And then ideally, you don't just learn the model, but also some sort of uncertainty estimate, some uncertainty quantification around the model. And then you feed this into a robust decision making pipeline. The robust control, robust optimization, whatever you want. This is the classical approach, how people used to do it over decades. There's also the growing trend of so-called direct methods, which essentially entirely bypass the notion of the model. There's no more mechanistic parametric model that explains the world. We now just look for algorithms that are compatible with the data that we have seen, completely bypassing any notion of there's a model of the world. And this is a growing trend, but it's not a new trend. I mean, people have looked at these 2 different philosophical approaches to solving problems for decades. But nowadays, this direct method gets overhyped. The central promise of direct methods, of course, at the end of the day, you're interested in the decision-making, in the control policy, in the feedback. You're not interested in the model. The model is just a vehicle to get. Of course, models are useful for many other questions. But when you're interested just in learning control policy, that should be easier than learning a full-blown model. That's sort of the central promise that's been. And this goes back decades and decades. One of the most famous examples is auto-tuned PID controls, invented in the 70s by Carl Ostrom and his PhD students back in the day. And now there's millions and millions of those out there in the field that from real-time data would tune the PID gains. And that's been going on for 5 decades. Okay, so that's nothing new. People have been playing this game for a while, and it's, all over industry. It's not a completely new hype. So this direct approach, when you bypass models, is definitely a viable alternative in some applications. You can argue from the application side where you say, sometimes models are just too complex to be useful. Okay, let me give you an example. Say you have a wind farm. You want to control the wind farm. You could write down first principle models of turbines, the mechanical part, electronics, the gears to drive. You could write down the fluid dynamics of the wake interaction between all the different turbines and blades, and come up with a gigantic nonlinear PD model. Would that be any useful? Not really, right? You cannot even simulate it. So sometimes models are just too complicated to be any useful. Another example is soft robotics. Yeah, you could write down first principle models for soft robotics, would be a PD with time-varying domain, but would not doing anything useful. So sometimes models are just too complex to be useful. Sometimes the environments are too complex to model. Think about autonomous driving, you can never model the environment. Sometimes you have complicated sensing modalities, like perception, or your specification is just very hard to encode. So in all of these options, maybe models are the wrong way to go, and you're better off by going the data-driven strategy. That's what people recommend. Other people argue from the side of shortcomings of system application. Maybe you should not identify models, let them be first principle or just parametric numerical models, because identification is very cumbersome. There's a famous survey that said that if you go to the industry and you want to design a control system, 90% of all the manpower and money goes into learning the model, 9% on the Kalman filter, and 1% on the control design. Long story short, you only do this if it's really, really important to come up with a model. Okay, so it's cumbersome. And models are not necessarily identified for the purpose of control. You identify a model to minimize a fitting error, like a least square error, but you don't identify it with the purpose of solving a control problem. So those are 2 different things. And you may have also incompatible uncertainty estimates. The least square identification will give you a variance error. It's a probabilistic parametric error. It's very hard to incorporate that in any control. And of course, finally, nowadays, when you just have brute force available, why shouldn't you use it? You could also take that pragmatic perspective, say, if you are in an application where you have a lot of data, computing power is also an issue, you may just crank it up. So these are normally the reasons why nowadays people prefer this direct approach, completely bypassing models. And that's, I argue from the perspective of control, but you could take a similar story for optimization or game theory, where they also have these. Okay, let me abstract this situation now a little bit into the world of mathematics, because when you look at these problems from the world of mathematics, you can see much more clearly what's going on. So we'll not use any formulas. I just want to phrase it all in the language of optimization, because then it's very clear what's going on. So the indirect model-based design pipeline goes as follows. You're ultimately interested in minimizing some sort of control cost. For instance, you have a robot going from A to B and you want to minimize the tracking error. Please track this reference. That will depend on your input, U, and maybe some internal state X. For instance, for F equal ma, you will need position and velocity. And this input U and the state X have to satisfy a model, typically in the form of a state-space model. Simplest case, A, B, C, D, linear equations. Now, there's something left in the box. What's left here? Well, what is missing if you really want to set that pipeline? Well, you have to estimate the state from both your input and your output. That's the output. So you have input-output measurements from which you identify the state, so things like a Kalman filter. But there's one more thing, namely model. Who gives you the model? Well, you learn the model again from data. So you get some data from inputs and outputs. I label data with D. Superscript D means data. So you get input-output data, and with this you build the model. So this is a very simple decision-making pipeline. Go into any sort of robotics problems, they don't just have these 3 layers. They have like 10 layers of different perception tasks and so on. But even in this simple pipeline, you see, you start with data, You build the model, build the state, then you have your state space model, and then you minimize the control path. So in a more formal language, this is a nested optimization problem. There's now 3 layers of optimization. Only the outermost is control design. The next innermost is estimation, and the most innermost is the system identification. So the 3 nested problems. And for the 2 outer problems, under some assumptions, we know the famous separation principles. We know we can design Kalman filter and LPR controller separately and put them together. That's fine. Maybe it's optimal, but not robust. So under some assumptions, you can make a certain equivalence case saying you can solve these problems independently and stack them up. But these assumptions are very fragile, easily break. And nevertheless, for the inner problem, there is no separation principle. There's nothing that says the best thing you should do is first learn a model, and then with the model, you go into your control design and estimation. That's actually not true. So it's the conventional approach, but if you care about end-to-end optimality, it's not optimal to first learn a model. These decision-making problems simply do not separate. And there was an entire field in the 2000s called ID for control, so identification for control, where they recognized that the best model, if you learn from data, is not the best model that minimizes your control objective. And that you should blend maybe the control design objective and the model application. So it's simply not true that you can separate these decision layers. That, of course, then gives rise to the direct approach. We say, okay, let's throw out the models. Maybe let's even throw out the notion of a state. Let's just work with raw data. And say, I want to minimize a control cost that depends on my inputs and outputs. And I argue the inputs and outputs should be consistent with the data you've seen. So that's much more lean, much more direct. It's called the direct approach or black box approach. The trade-offs now with you see these 2 formulations more abstract in the language of mathematics are very clear. This here is modular. Modular means normally easy to implement, easy to debug. This is end-to-end. Turns out practitioners sometimes prefer the modular approach if they know the individual ingredients, but sometimes they also want the end-to-end where they just press a button and things happen. This here is generally suboptimal. It's not true that you can do these things sequentially. Sometimes you can. This has the potential to be end-to-end optimal, get the best out of it. That's why often reinforcement learning can beat control, because they don't have the notion of the model in between. But of course, it's very hard to make this here any sort of tractable. Tractable meaning, for instance, from the language of optimization, it's very hard to formulate this as a convex problem. Whereas here we have a whole bunch of small problems, each of which is known how to be a tractable, and can be convex. So that's sort of the abstraction and the direct indirect approach. Of course, now I just told you there's sort of certain equivalence case, that is, we do not account for any uncertainty, any noise, and so on. Ideally, in all of these individual optimization problems, you want somewhat to account for uncertainty and propagate this to the next higher layer, which also is very hard here. Like get any sort of uncertainty from the data that translates to an uncertainty of a model, and that you use here. It's by no means easy. It can only be done very conservatively. Let's further zoom into this question. So people have debated, not just yesterday, but in the last 3-4 decades already, these 2 approaches. Should it go direct? Should it go indirect? People in adaptive control, people system education, and I read through a lot of this more old literature, and I compiled all these arguments a little bit. So here's normally what they come up with in terms of the pros and cons of either side. As said, models are useful. Models are useful for control design. We've got many powerful model-based methods for model-based optimization. And models are useful beyond, of course, for simulation, training, analysis. But as said, some models are just too complex to be useful, especially when you go to high-dimensional and nonlinear models. So that's the con you can put in. Here people argue the indirect design pipeline is modular and thus easy to debug and implement. But often experts like the end-to-end approach. They don't want to deal with tuning the hyperparameters of the ID, of the Kalman filter, and so on. They just want, give me a policy that works. You can, on a high level, interpret the model learning, identification, as 2 things. Think about identification as noise filtering. It takes raw data, it chops the noise away, and produces for you clean data in the sense of a model. You cannot do this in the direct approach. You need to somehow do this in the design process. And here's another one. People call this bias, enforcing a physical bias. So if you have any sort of information about your model class, you can enforce this bias on your identification. So if I know there's an F equal ma equation, Newton's second law behind it, I can use that information in my learning process. Okay, so that's useful. It turns out in practice, but what often happens, it's, you get a bias error, meaning I learn a model, say it's a LTI system, linear time variant of order 5, and I fit that to the data. There is no LTI system of order 5 in the real world. So whenever you inject your bias of this model, should be the right model class, you encounter this bias error. That's again where the direct approach can win. You will never make a model class assumption. And there's some of the other points that I already mentioned. So it's hard to propagate uncertainty. There's no separation principle. But I'll just repeat myself. So there's lots of pros and cons. The list actually goes on. There's no universal conclusion. People kept on arguing about this for multiple decades. And the answer is always it depends. Maybe at the end of the lecture, at least for the problems we look at, I have a more clear answer for you. But if you're interested in this thing, I wrote up a discussion where I compiled all these thoughts. You click on the links in the slides in the Control System magazine. But it's a long discussion. People have argued about it for long. So, before actually telling what we will do, I first want to tell a bit of a story of classical direct approach. Nowadays in modern language, they call it dictionary learning for people control. It goes as follows. You learn a dictionary. For instance, you have a robot. You learn how the robot moves its arm sideways. So that's what they call motion primitive in robotics, for instance. You learn how your robot lifts its arm. That's another motion primitive. And then you do linear combination of this and that, and you get this. Essentially, you learn some sort of basis functions from your data. And you can do this, and many people do this nowadays. They go under different names like Krugman operators, like mode decomposition, and so on. And then just you optimize over your dictionary in real time using any predictable approach. This is what you would find the most sort of, you go to NeurIPS or ICML or so, and you look at the people doing control at these conferences, they will do these types of things. It turns out that there's a huge theory practice gap. So this works sometimes it breaks, but the theory is in the very idealized assumptions and not really understood. So let's bring that back to the LTI case, linear time invariant systems. Maybe that's where we can start actually the school. Maybe let's look into a linear time invariant system and think about, can we combine trajectories we've seen, formulate a new trajectory? And let's look into a particular case. So whenever you see these boxes on the slides, this is where I start writing things. You can copy or not. I can also afterwards provide you a sanitized version of what I write. So we'll now look into an LTI system. Okay, so we know this guy here is linear and time invariant. LTI. This thing is fed with a zero initial condition. We give an impulse at time 1. And here we collect the impulse response. Good?
Yeah.
All right. So, as you know, the impulse response in the LTI system, we normally call it, if you take a bachelor broadcast, it's normally called G, or in the Laplace domain, G of S, G of j omega in the Fourier domain. So what you get from U being a delta at time 0, and a 0 initial condition, x of 0 is 0, you get a particular output time series, y of t, which we normally give a name. We call this one G of t. This is the impulse response, which is normally a signal that goes like G of 0, 1, 2, and so on. What is nice, if you had the impulse response to your system, you can now generate any other response. Okay? So the response to any other input u of t is given by what is called the convolution. So you probably learned this also in your bachelor courses, that y of t, if you put in any input, will be the convolution of u of t, and g of t will be the sum ranging, say, from power 0 to time t to minus 1. And here's a g of t minus tau times u of tau. You've probably all seen this formula in either continuous or discrete time. the main takeaway is if somebody gave you the impulse response, you can now generate any other response. Well, and that's where you can actually start data-driven control. So if you had the impulse response in your library, if there was one motion primitive that somebody gave to you, if you had really recorded that, like you hit the system impulse, you record the output, then you could now compute any future trajectory, right? So you could really say now the response, any new input, let's call it u future of t, is actually equal to y future of t being whatever you have in the library times this input, right? So it would be in this case in the sum of power 0, d minus 1. And here if your collected signal, yd, d minus tau times u future. So you could do complete data-driven control. You could now start optimizing over this u with t. Somebody gave you that. So it turns out actually that's how history went. So this is just another way of writing this. So I can now predict any new future output to any future input just by doing this convolution with the input. So it turns out this was invented in the 1970s in a company in Shell. They called this back then dynamic matrix control. And out of that came model predictive control. So historically, the idea was actually the start of what is nowadays called MPC. And now, interestingly, 5 decades later, people will go back to that original idea again. But that's how everything started, right? So you record the impulse response, and then you optimize over future trajectories with the impulse response. And that's the simplest case of a direct approach where you use a pre-recorded trajectory to generate all new trajectories. So people have done that in industry. So I asked my colleague, Manfred Moray, who apparently back then knew these people quite well. And then afterwards, he invented MPC out of this. They said it never worked. They did it for 2-3 years in Shell, in the company, but they never could get to work. Why? Because in principle, you would have to have the infinite impulse response with 0 initial condition and no noise, nothing, right? And in practice, that's not the case. In practice, you always have corrupted data, you have finite data, and you don't have impulse response. It's impossible to make this dependent on initial condition, to make it stochastic, or to make it nonlinear. So that didn't go any further. And then 2 years later, they invented the model-based setting, the MPC, and that obviously still survives today. But I want to tell this as a nice story of how can you generate a data-driven controller out of just recorded data in a very simplistic setting. All right. So much about the motivation. I told you a little bit of a story about data-driven control, zooming in from the outside, highlighting the pros and cons of doing it direct versus indirect. And I gave you this little case study. So what I want to tell you today is a particular method that we invented that we just coined with a fun name. We called it a deep C, but we only used the word deep in it to make fun of our computer science colleagues. But the word stuck, so people still call it deep C in papers nowadays. So the acronym is for data-enabled predictive control. It is based on a very abstract notion of system theory called behavioral systems. I will not teach that to you, but just one single result of that we need called the fundamental lemma. It turns out this by itself is enough to make a full clean story for linear time invariant deterministic systems, and it just takes me like 1 page to do so. But it turns out this is not robust, so we need to robustify this. And I'll tell you also how to do that. And I'll show you case studies mostly from the power systems, power electronics world, and wind generation, because that's my main application that I work with. But we'll also have other case studies, like we also have tomatoes. So stay tuned for that. People use that in the Netherlands. They use this method to grow tomatoes. But it turns out tomatoes are not different from LTI systems. This literature actually is quite on the exponential. I think that number is even outdated. There's more than 3 archive papers a week on deep C. It's a lot. If you want to get into this and you start reading the archive, you will just get lost. So I don't recommend doing this. If you really, other than following, of course, here, I suggest you look into this sort of tutorial publication, which just try to collect all the basics and important things together, and then you can go on your random exploration. But it's a quite busy area. Okay, let's get into it. Before doing so, everybody's fine with the high-level picture, why we do this? All right. So organization, we'll use the board. I'll cover most of the basics, but if you have any questions in between, just throw them at me. I hope I can answer them. Actually, most of the stuff I tell you, we now teach in Zurich in the bachelor. So in the bachelor, we have a course called computational control methods. And these methods are sufficiently simple to teach them actually to bachelor students. So there will not be a lot of math overhead. So reach out to me if you want any material. And we'll probably take a break. Actually, I put them in at 90 minutes actually a few days ago, but I was happy that there was actually exactly 90 minutes. So before going into the myths and the methods, I just, maybe as a last selling point, I want to share an example, one of many examples we can solve, and then hopefully convince you that this is a powerful method. So here's my favorite application domain, power systems. These circles here, this disk with this squiggly arrows, those are synchronous machines, big chunk of irons, rotating magnetic field. There's a sparse transmission network connecting these. And you shouldn't be surprised when these things are oscillators and there's a sparse network in between that when you just measure power flows in the tie lines, you see these oscillations. Quite common, all power systems in the world. These oscillations are desirable, you want to dampen them because they can go unstable, they cause losses, they trigger protection. So one way how you can solve that control problem is you would measure these oscillations across your tie lines. So you measure once the power flows here and here. You take these measurements and you send them through some controllers. In this case, this particular line is a high voltage DC line where you have power converters at both ends. And you can tell the power converters, please dampen these oscillations by appropriately modulating this up. That's a quite standard control loop. It's called wide area damping control, implemented in most power systems, either through power converters or through controls of the generators. So for this particular power system, which is still a toy example, by no means as large as a real power system, it's already a challenging control problem. We have 200 states. We only got 8 measurements. It's nonlinear, noisy, stiff, a lot of time scales involved. You have very tight input constraints because power converters don't like overcurrents. Any 10% overcurrent will fry your converter. They have very tight constraints. And you want to solve this problem with 2 decentralized controls. So it's a very hard control problem. I tell anybody, please solve this and write a proof that it works. Nobody will be able to do so. If you give this to a power system engineer, ask them, well, can you design a damping control? So they'll probably tune some sort of size of filters, like a PID and washer filter, and start tuning those until they get damp them, and they can roughly make it work. It's a hard problem, and you can never satisfy it. So what I want to do now, I want to solve this problem without a model. Okay. Biggest hoax in power systems, when you read all the power system books and papers, they're all academic, because in reality, nobody, literally nobody, has a dynamic model for power system. I would challenge that. Even in China, where you think they've got the most advanced system in the world, they don't have good dynamic models of the system. Okay. It's just a fact. Nobody has a dynamic model for power system. Why? It's large scale, a lot of different entities, generation owners, system operators, different ones. They don't like to share models. They don't want to share data. And even if you had the model, it would be outdated immediately because the operating point changes, and you couldn't even simulate it in real time. So there's a good case why you want to solve such problems without having a model. Okay, so whenever you see power system case studies, when you write down some model and do some Lyapunov analysis, that's really textbook. In reality, you can't do this. So here's what we want to do. So we'd like to collect these oscillation data, feed this into an algorithm, and this algorithm should ideally dampen these oscillations. And ideally, I want to find a method that, first of all, I can teach a bachelor student that works reliably, not just in this example, but in all examples. That you can implement on a, you don't need a GPU, but you can implement on a controller, a small microcontroller. And ideally want to be able to certify this, under some reasonable assumption, I can show this works. That's sort of the dream goal where you want to get to. Obviously, we don't get there, but I think we have a promising path, how we can do this. Ideally, I want to automate myself. So that's a yes. So the question online is the oscillation damping tailored for inter-area or also for local oscillations? It turns out it can do either or. I'll also show you later on examples where you do local oscillation damping, but you have to stay tuned for a little longer. But I wanted to essentially tell you, whatever you learn now is a method that we teach in the bachelor, and they can solve these complicated problems without models. And now you should be suspicious. Who is this crackpot here? Right? Because that seems too good to be true. Nobody would ever do this, right? Nobody would throw a shaky data-driven method on the world's most complex, most expensive engineering system. Nobody would do this using the world's biggest actuators, like gigawatt-sized HVDC units. Any of all these issues, like real-time computation, safety, stability, constraints. So it turns out, actually, there's now at least 3 companies that implement these things. So the first one that approached was Hitachi ABB that saw our archive paper, said, hey, we found this thing online. This sounds really cool. Can we try it out? So we did. We sent them our code. So they had their own simulators and some proprietary Siemens software, PSCC, and we sent them a piece of Python code, and they wrote this somehow into their simulators in their own language, in their own case studies. And a few days after sending their code, they came back to us with these pictures, say, hey, it works. And it worked black box, right? So they were super amazed by it. And the only reason I want to tell you this, somebody believes it's actually useful. It is not just math. You can really implement this and make things work. All right. Guess now I owe you what is behind, right? Okay. Did I increase enough excitement here? Let's go into a little bit of bachelor control, just quickly reviewing representations of LTI systems. As you know, there's different ways I can write linear time-varying systems, like frequency domain, state space, or ARX models. And I quickly want to review that, only to tell you afterwards we'll throw all of that away. But it's important that we see it once. So the standard one, when you go to some sort of time series analysis, they would model a linear time-varying system as something called ARX. So A stands for autoregressive. And X stands for exogenous input. It's what in continuous time we just call a higher order differential equation. In discrete time, this would something like this. I'll just do everything by means of an example. It would be something like y of t plus 2 plus some other coefficient, for instance, 2, y of t plus 1 plus 3 y of t. This instance for u of t. Some time series, u of t, y of t that are related by these coefficients and time shifts. Okay, that's called an ARX model. This is what people would work with in the system modification world. What normally people do in control, they go from this ARX to what is called state space. So everything just written as a first order equation. That is, you design a notion of state, that is your memory variable. So x of t would then be plus y of t plus 1. And then we'd write down the state space equation. So x at time of t plus 1 is equal to some matrix times x of t plus some other matrix times u of t. And you have y of t being another matrix times x. So from here, so we have x of t is y of t. So from here 1, 0. There will be here 0, 1. And x of t plus 1 is y of t plus 1. Then there will be here a minus 3, and a minus 2, and a 0, and a 4. So this is one way to write on the model. We normally call this just ABCD, these 3 matrices, or ABC. Alternatively, you can go to transfer functions. Essentially just apply the C transform, which I realize nowadays is not taught anymore, but it's just a discrete time analog of the Laplace transform, which will give you something like this. There's a y in the frequency domain, so y of z is related to u in the frequency domain. U of z, and in between essentially is your difference equation with z squared 2z plus 2. That's another way of writing. If you don't know C transform, that's fine. Just think about the Laplace transform in this group. Now, what I want to maybe carry home is the following, that however you choose to represent it is the following. These are all parametric representations, meaning you parameterize the model by some parameters. In this case, it would be the numbers 2, 3, 4. And they're also what is called kernel representations. Okay, maybe that's a more important point that I quickly want to emphasize. Why is that? Let me just copy and paste this equation. Continue here. We can rewrite this, that it's really clear that this is a kernel. Kernel meaning something that you multiply so that's equal to 0. Okay? So let's introduce a time shift. Let's call it sigma. What does sigma do? You apply sigma, say, to y of t, and you get y of t plus 1. It's just a time shift operator. So I can write this entire thing as follows. I can write this as sigma squared, 2 time shifts, plus 2 sigma, plus 3, 4 times y of t, u of t is equal to 0. Okay? So I take my space of signals, u of t, y of t, and I find something that I've multiplied from the left with, and it's 0. Okay? This is what is called a kernel representation. And all of these are, in one way or another, they're ways of writing these kernel representations. So it's just a left annihilator of the space of time series. What will be a big philosophical shift and what we do later on is we work with image representations. We don't look for things like models that would take the set of all time series and be orthogonal to that, but we'll work with only this part. Okay. I'll later tell you how this is, but I just want to put this in contrast of standard models. So that's not our idea. It goes back to this notion of called behavioral system theory. So if you ever want to study behavioral system theory, my first recommendation is don't, because it's written in a level of mathematical abstraction. It's very hard to read. Also, the main guy that wrote it, Jan Willems, he wrote his papers in at least 3, 4 languages. So unless you can speak English, Dutch, French, German fluently, you cannot read his papers because he wrote them in these languages mixed. In any case, so there was this group in Groningen, mostly led by Jan Willems, that invented behavioral system theory. Behavioral system theory is a very abstract branch of systems theory, and it says the following. It says, we don't want to work with any of these representations. We just want to work with systems as sets. We want to work with systems like here, just sets of time series. We don't want to work with other things, just time series and sets of time series. So in the most general way, and you don't need to remember that, I just want to give you a little bit of insight. I would say dynamical system is a 3-tuple. It is the set of integers, so the positive integers, which is discrete time axis. Then you have some sort of signal space, okay, Rn or so. And then you can create the set of all time series. So W to the power set is the set of all discrete time series in W. So it's the set of all time series you can construct. But now instead of taking the set of all time series, we take a subset, which we call the behavior. So in words, the behavior is your set of trajectories the system can express. It's just a set of time series, and you work with that abstract set of theoretic notions. And all the books and papers are written in that particular abstract notion. That's why they're very hard to read. It's pure set theory. But it turns out that's a very useful notion. So let me make it a little more useful and tell you what it's about. A dynamic system, let's make it a little more precise, is linear. If your signal space is a vector space, and your behavior, the set of all trajectory system expressed is a subspace of the set of all time series. For example, this here would characterize a subspace of the set of all time series. That's one way to think about it in this abstract language. Okay? A linear system is a subspace instead of all time series. And it's time invariant if this behavior is invariant under a time shift. Say shift Wt by +1 and everything remains the same. Now, why is that useful? It's a little bit how computer science people think about dynamic systems. So when you go to a machine learning person and they ask me, can you do something, or can you learn a dynamic system? They would say, sure, let me just take my data set and fit a low dimensional object, like a subspace and data set. They wouldn't think about models, they wouldn't think about causality, they wouldn't think about the time axis. They would just fit a low dimensional feature, like a subspace, into your data set. That's why this is so much compatible with data-driven control, because you never look for a model, you just look for subspaces instead of all time series. So what is the data to remember here? Going from all the details, just to give you a little bit of an insight. A linear system is just a shift invariant subspace of the trajectory space. That's what we're working with. And it's up to you how to characterize subspace. You can use models, as I've shown you before. Models in that language would be kernel representations. Or you can just use raw data to characterize these subspaces. And that's eventually what these methods will do. Just use raw data and from the data build subspace. So let's look a little bit again to the LTI case and get some insight into the space of trajectories in the LTI system. And I'll do this in a language that you use, as a state space system. We understand a bit better what's going on. So let's look into some properties of the LTI trajectory space. And let's work with something like a model, just to get us familiar with. We have a model in state space, something like x of t plus 1 equal to some matrix A, x of t, plus b, of t, and y of t, cx of t, plus u of t, and we have initial condition x of 0 is equal to some x in. And now we could just roll out the solution of that equation. I'm sure you do this often in your life, so I'll keep it short. So you could just construct a solution. We'd say x of 0 is equal to x ini. X of 1 is a x ini plus b u at time 1, or b u at time 0, sorry. X of 2 is a squared x ini plus a b 0 plus b at 1, and so on, right? So the standard. And then y of t is just c times x of t plus d of t, okay, which gets you to the formula that y of t is actually equal to c times a to the power t times xe plus the convolution sum over tau 0 to t minus 1 c a to the tau b u of tau plus d u of t. And I'm sure you have to study this very often in your life. That's why I went fast through it. So that's sort of the standard linear system response. So let me now write this in vector notation and look at this response as a set of time series in the trajectory space, and let's characterize the notion, properties of this subspace, in particular its dimension. Okay. Before we go to the dimension, let's just fix the dimensions here. So for me, x lives in Rn, and u lives in Rm, and y lives in Rp. So in vector notation, this is how people, for instance, subspace systemification would write these things as follows. You would have your vector y of 0, 1, 2, all the way to y times t is equal to, and here would have the matrix, which you probably all have seen, C, CA, CA squared, all the way to CA, which is the terminal index of capital T, CA to the power t minus 1, and times xe. So this is what is famously called the observability matrix, or extended observability matrix. Call this guy here OT. And what is here is what is called the impulse response matrix. So VD, you would have a CB, D, CAB, CB, E, and you go down the diagonals here. And the last row you would have here a C, A to the P minus 1B, so on. And this gets multiplied by your input. Okay? U of 0, all the way down to U of. So this is, let me just check my notes here that I have the notation right. This one I call here CT. That's the extended impulse response matrix. Good, all things you've seen. Are we going too slow? Good. Go faster. If you don't say anything, I'll just do it my way. Okay. So we can write this compactly as follows. So compactly, you would say something like your Y is equal to extended observability matrix times X ini plus your impulse response matrix times U. This is how you would write this compactly. Quick review of one fact, observability. Okay. Observability means the following. Can you reconstruct the initial condition? Okay. Namely, X ini can be reconstructed from Y and U, in particular from this equation that relates here Y and U. Well, that's true if and only if this matrix is full rank. That is, X in is not in the null space of that matrix. Okay. So it can be reconstructed from equation if and only if the rank of the observability matrix OT is equal to n. And we know we don't have to go down to, say, a length 100 time series. We know this rank conditions are satisfied. Just go to n steps. Famous result, did you call them? In particular, to make this more concrete, the smallest integer L, so that the observability matrix OT has rank n is called the lag of the system. And you probably know that the lag is equal to n for a sizer system. So if you have only one input, one output. But say if you have multiple outputs, you could have the case that L is less than equal for a MIMO system, right? So you may be able to reconstruct the initial condition without going back 2 steps in time. Okay. I want to repeat this because this nowadays is not being taught anymore. That's the lag of system. But it's useful to say. It's just how many times steps go back to reconstruct the initial condition. All right. What else? So just a quick conclusion that I want to note down then. If somebody gives you data in the past, so given past data, and I'll reduce this to introduce a notation, namely U ini should be something like U0, U1, all the way to some U of time T, and Y ini, which is again a time series Y of 0, all the way to Y of T ini. We get that X ini can be uniquely reconstructed if and only if your data's time series is longer than the lag of the system. All right. So why do I introduce all of this? Because now what I really want to get to, I want to characterize the space of trajectories, namely, what's the dimension of the subspace? So the dimension of the LTI trajectory space. And then we'll again switch the slides. So the question is, any x ini in Rn, what is the dimension of u y, which would be your u of 0, or u of t, and y of 0, or y of t. Okay, what's the dimension of the trajectory space? So we know we can write this follows. I can write this as a matrix. And here again, I will put x ini in u. You know, x ini lives in Rn and the measurement condition. U lives in the space of the input, it's Rm, and then this t time series sits in Rmt. What is in the matrix? Well, on the upper right, there's a trivial block. It's just identity. It just says here essentially u is equal to u. What is down here? Here would be observability matrix, OT. And we already conclude now this column has rank n for t greater than the lag of the system. And here would be the impulse response matrix, CT. This column always has full rank, because it's the entity upper right. This always has rank n constant. And conclude, the range space of that matrix is of the dimension of this column, which has rank n, this column, which has rank nt. Okay. The dimension of the behavior, dimension of uy, is equal to m times t plus n, or your t being longer than the lag of the system. So this was a very, basic linear algebra derivation, only to tell you what the dimension of the trajectory space is. But now you know for a linear system, finite length trajectories, what you should look for is a subspace that has dimension of the size of the initial conditions, the length of the time series, times the number of the inputs, provided your time series sufficient long. And now, why is all of that any useful? It goes to the fact that you can represent an LTI system only based on matrix time series. This is famously known as system modification or signal recovery algorithms. And it goes as follows. So normally if a time series, u and y, you would characterize this one by models. So you would say your u and y satisfy a difference equation, or what we now call a kernel representation. We say u of t plus 1, y of t plus 1 are related with a bunch of coefficients, b0, a0, b1, a1, and so on. So this is the kernel approach. Let's now take the image approach, so we can take a orthogonal complement, and not just pile up data. I take data, I put all the data in the matrix. In the first column of the matrix, I have experiment number 1. Second column of the matrix, I have experiment number 2. Third column, I have experiment number 3, and I go on. Notice, if I were to multiply this matrix from the left by this vector, which is the coefficients of my ARX model, this would be 0. Because multiplying this guy with that guy gives me exactly this equation. So this is a kernel representation. This would be an image representation. And the question is, is there like a one-to-one relation? Just given data, can you uniquely reconstruct the model? That's true under assumptions. And these assumptions nowadays are famously known as the so-called fundamental lemma. When I first read the name fundamental lemma in a paper, where the author, Jan Willems, referred to a previous result of his own as the fundamental lemma, a little bit cracking up. How can you be so pretentious? But I appreciate it now, so he had a good point. It is fundamental. It goes as follows. You have a black box. You only know about the black box LTI. You have data. U lives in Rm. Y lives in RP. You give yourself some complexity parameters in a black box. So you say the black box is any LTI system of order at most n and lag at most l. You take this set theoretic perspective and say, I want to characterize a set of all trajectories. So I look into all u of length rm times t, y of length rp times t, and then normally write down an ABCD equation to characterize that set. That's sort of the parametric set-based approach. And what the fundamental lemma says is, don't do that. Instead, do the following. Just take a bunch of experiments, put them in a matrix. Every column is raw data. Every column is one experiment. And these two sets are identical. So to put it in words, everything you can do with a model, at least in that set theoretic space, saying I want to characterize a set of all trajectories, I can do perfectly with other models, just taking experiment, lumping them in a matrix, and taking the span of that matrix, the range space. And I argue they span the same set. Well, that's too good to be true. That is true if and only if that matrix of low rank, and we know what the dimension of that matrix should be. I already derived it. We know that the space trajectory we're looking for should have dimension number of inputs times length of the time series plus state space dimension, all t sufficiently large. So this is why I derived that for you, that you understand where this condition comes from. But now, actually, I only have one request. So if you don't remember anything from what I tell you about in these 2 days, just remember that one. Just remember that you can work with models, or you can equivalently work with raw time series put into a matrix. And everything, literally everything anybody's ever done with an ABCD model, I can do also with pure time series. And there's a one-to-one correspondence. Take any result you take in any control course, any linear systems theory book, you can rederive now the same result just using raw data. And that's the link in between, the fundamental lemma. It says the set of trajectories can be spanned either by raw data, put into a low rank matrix, or by a model. And that's why there's like 3, 4, 5 archive papers a week, because people are very busy doing it. But essentially, this result, dating back to 2004, established that link. People forgot about it for 20 years almost, but now it became very hard to things. That's the main takeaway. And if there's anything else, you can forget the rest as long as you remember this equivalence here. Because now you can do everything you want. In Word, it says you can construct all trajectories you want to construct, the entire trajectory space, by having seen a finite library, finite basis. The only assumption is that that matrix has the right span dimension, so m times t plus n, the dimension of this trajectory space. So the result I showed you is the result that we proved. The original result by Willems from 2004 was a little bit weaker. It was only sufficient. It had some extra assumptions, which I'll not go into now. But it's really their result. They discovered this like 20 years ago, and now the world follows up. And now you maybe appreciate why they call it the fundamental lemma, because everything people do with data, like commercial primitives, subspace identification, dictionary, and so on, they all rely on this equivalence. So you can take raw data and do the same thing as you could do with models under that assumption. And if you go to people from subspace ID, they would say, yeah, but we knew this already before and stuff and so on, but it was never as clearly stated as here. And people have been extending that, take a favorite system class, like differential algebraic, delay, LPD, or even nonlinear class like Volterra series or Wiener Hammerstein, I don't know what, flat systems. People have been extending this type of result to these other system classes, are very busy doing it right now. Okay, so it can be done, has been done, people are busy doing it. People developed other proof methods and so on, but I think the proof I showed you is still the simplest to explain. Okay. We now take a deep breath. So that's the main thing. Are there questions so far? Yes.
So I have a couple of questions.
Sure. Sure. Definitely. I agree. So 2 answers. One is, of course, assuming everything is linear and deterministic, so you have no noise in whatsoever, then of course you'd be interested in all these columns being linear independent, right? And so you want to run experiments to give you essentially orthogonal columns, right? I don't know a way of doing that, to be honest. Sure. There is a sufficient condition which says if your input data is persistently exciting, then also this matrix will have the right rank. But it does not make a statement about the lower single value or whatsoever. It's just a quantitative statement. The second comment I want to give you, while this is a beautiful result, it completely falls apart if you put a tiny bit of noise or nonlinearity in the system. Because if any nonlinearity noise, this matrix is always at full rank. And it's useless. So that's what the rest of the course will be about, among others. How do you robustify all of this in case you have a stochastic system, in case you have nonlinearity? But what you're referring to, this input design problem, how to get ideally a well-conditioned matrix, is largely open. There's only qualitative results on rank condition. Mm-hmm.
So if you run, say,
Yeah. I mean, again, for the clean case, you don't need infinitely many, you just need as many columns as rows. But of course, now you can run more and you get more columns. So what do you do with more columns? You can average them. Averaging reduces variance. Variance goes down like 1 over square root of the number of experiments. Or you can do the most important one, to select the most orthogonal columns. That's definitely what you can do. Yes, you can do this, but I've not seen a theory that quantifies like how much better you get. But the standard thing people do is just collect many of them and then do some sort of SVD type analysis. But it's mostly heuristic in terms of they cannot certify how good it is. Yes.
So I have a question. So the motivation from using that is avoid having a model altogether, using only the data, right? But this what you show here is based on an assumption. They appreciate that you are gonna relax it as we want, but
sure, this
still, but for the LKI, this is one part. The second part is that you know the order of the system. Right? So what happens in practice? Do you just add data until you see that the order is?
It turns out for the control design, that's almost irrelevant. I just take the data as is. But if you care about the order, you would just give yourself n upper bound on n, right? And then keep on doing it. But it turns out we will not need these numbers later on for the design process. We just take the data as it is. And this will actually be, I can already give a spoiler alert, I can beat any model-based design procedure. Reason being, you have a model class, you project the data in the model class, you need to assume an a priori order. Like the world is LTIF order 5. Whatever I'll do later on, I just use the data matrix. I don't make the order assumption. And that's why I can beat models that rely on having a certain order. But yes, for the theory, if you really care about this rank condition and you want to satisfy it, you need to give yourself these numbers, or at least a bound on these numbers.
Is the model provided that you make the assumption to identify this?
Yes, correct. But you're right. I mean, the result relies on knowing these numbers, but it turns out how we later use it, it's irrelevant. Good. That goes back to your question, input design. So that was the original paper written by the behavioral guys. They were taking the input perspective and asking, what are questions in input? So they get the full rank conditions on the data. And the assumption they made essentially was called persistent excitation. That is, they assumed the input signal, UD, has a particular property that if you put the input signal into a matrix, this matrix is a full rank. What is this matrix? In the first column, you have time series u until t plus 1, until t. Second column, you shift everything by plus 1, so you have a u2, u3, and so on until u of t plus 1, and then you keep on continuing. You just always do a +1 shift. This is called the Hankel matrix, and you assume this Hankel matrix has full row rank. What does this assumption imply? If this matrix is full rank, notice this here is the number of columns. So you want the full rank is the number of rows. So the full rank is m times t. So essentially what you need is that the number of columns is greater than the number of rows. So you need the TD, the length of the data sequence, times the horizon you want to predict, plus 1 be greater than mt, which implies that your data TD is sufficiently long, the data length. Further, you want this, of course, to be sufficiently rich. If all the columns were linearly dependent, it wouldn't happen. And then the original result, it's not a quantitative result, it's more qualitative. On the rank condition, it says if your LTI system is controllable and you have this persistent excitation, that means your input signal is sufficiently rich that it has full rank, then also your data matrix will have the desired rank conditions. So that's sort of the original result by Willems and his co-workers in the input centers. Notice again, this result is purely academic because in practice, rank doesn't mean anything. When you have any tiny bit of noise, this matrix always has full rank. Before we go into how we use all of that, maybe quickly a word on data structures. So what you can do, we construct the matrix of different things. One is what I call the trajectory matrix, which is the one I showed you. So let me call this, for instance, H of W, where W is the U and Y together, so UD, YD, which I just construct as follows. So you have the first experiment. Here we have the second experiment, and so on. So you can just lump up a bunch of independent experiments. This works well if you have a system that you can experiment with, which you cannot do all the time. So people developed other structures. Another one is that they call the page matrix, which goes as follows. So here your H of W now is not independent experiments, just one long experiment. So you have here a W1, W2, all the way to WT. Then you continue time series here, WT plus 1, WT plus 2, W2T, W2T plus 1. So this requires one long experiment. There's these two. It turns out you can also just use one short experiment, and then you build the so-called Hankel matrix. Where you just take one short experiment and you rely on time invariance that you can just shift the trajectory. So you write W1 until WT, and then you just shift by plus 1, you have a W2, WT plus 1, W3, WT plus 2, and so on. Because any time shift of trajectory is again a trajectory. So this only requires one short experiment. But of course, you're not as orthogonal as in the other cases, your columns. Or you can do any combinations of those. Because as long as every column has a valid trajectory, you can throw them together as you wish. So there's different things that people play with. I also have a keyword here on pre-processing. Namely, often your data is noisy. And I'll tell you in a second what we do with noise. But what you could also take the perspective is you just pre-process the noise. So pre-processing of noisy data. Turns out we will not do this, but it's still instructive to see it once. What's the issue? If WD is noisy, then all of the above matrices will have full rank. And not the row rank properties we decided. So what you can do is you can just go through a literature that's called low rank approximation. And that literature consists again of thousands of books. So you can choose your favorite method. 99% of them will always do the same thing, namely called singular value decomposition. It goes as follows. So low rank pre-processing. Just find the closest matrix of low rank. So you say minimize over some W tilde, where you say your W tilde is close to the original data, but you want the rank of the data matrix, H of W tilde, to be the desired rank, ML plus N. It essentially is find the closest low rank data. And the standard solution to this problem, at least if your matrix does not have a structure, but it's an arbitrary matrix, it doesn't have a Hankel structure, it's just singular value threshold. Standard solution is to take an SVD of your data matrix, throw out all close to zero singular values, and you only keep the largest ML plus N singular values. And you can argue this is optimal in a certain metric and so on. But then that is actually optimal if the matrix is unstructured. So there's no sort of conditions like in the Hankel case or no linear dependence. So it looks like a good thing. But of course, in our case, this does not work so easily. So it does not apply, at least not rigorously, because time series are correlated. Meaning whatever happens at time t plus 1 depends on time t. That's the notion of dynamic system. Okay? So that's why this is a heuristic that sometimes works, but I've seen it breaking more often than working, to be honest. Okay, time series are just correlated. You cannot assume that one element is independent. Nevertheless, that's what people do standard. So we have about 10 more minutes here, I guess. So let me now tell you what I want to do. So this is just we're still in the warm-up phase. I just showed you the fundamental lemma. You can use raw data to represent your trajectory space. People have been busy doing that. So the original paper by Jan Willems was submitted 2004, then 2005 got published. That's fundamental lemma. The version I showed to you is this generalized low rank version, the if and only if, which we wrote in 2020. The person mostly carrying that literature was Ivan Markovsky, but nobody listened to him for 20 years. Now they do. When you talk to the old people, either in subspace methods, subspace at E, or in adaptive control, they would tell you, oh, we've known all of this long, long ago. And it's true. You can go to some old papers, say from 86, 89, 99, where they were more or less using similar type results, but nowhere as clean stated. But I still regard this as the central result. What people have been doing is the following. The literature sort of split up into explicit feedback design, namely how to use this result to determine, similar to a model-based way, like U is minus Kx, the optimal LQR gain K. Okay, that's most been driven by Claudio de Persis, Hank van Baarde, and their co-workers. I will maybe cover, or I'll probably cover part of that tomorrow. What I want to do now is how can you use this for implicit control design, in particular model predictive control. And we'll use this fundamental lemma in its low rank version. I told you it's purely stylized, works for the LTI case. So we need to robustify it. And the way to robustify it is essentially for what's called regularizations. And then we go with this one into MPC, model predictive control. And then we get a range of results that you can get either this way Or you can also take detours and get to the same results another way once you know what you're looking for, which again, people are doing. But that literature is branching out every day more and more. But I'll give you essentially this path. So before the break, I want to set up primer for MPC, particularly output MPC. Quick hands up, who of you knows MPC? Most? So let me give you a short version of it. So MPC, you have a model, ABCD, and then you run the model forward in time. Predictive control, you predict forward. You run this iteration forward in time, so from time x1 until t future. And now your optimization variables are u, x, and y. You say, I want to find the best trajectory. And you formulate best through some criterion. Will not matter for today's lecture what the criterion is. The standard will do some sort of tracking criterion. Say your reference y should track, so your output y should track a reference r with minimal control effort. And you have some weightings on these norms. There could be one, but you can take any others. And you run this forward from time 1 until t future. And you can put constraints in place, which is very important in any sort of industrial control system. That's where often this is a go-to method next to PID. And that's how the problem is normally presented in all papers. Then, if you ever go into the lab and want to implement MPC, you realize you can trash all of these papers. Why? Because you somehow need to initialize this recursion. If you don't have the state, you cannot initialize it. So you need to do on the side essentially a common filter or so to initialize the state. So that's where the output comes in. One way to do this is called receding horizon estimation. So this part here stands for your output. And what you do now is you take again your ABCD model, but now the time index k runs backwards. So k is 0, -1, -2 until some minus t-ini -1. And as I've told you, if your t-ini is greater than the lag of the system, then you can recover the initial condition. So that's the estimation part. And this would be the predictive part. But essentially what you do in MPC, you run your ABCD model both forward and backward in time. It turns out this is not a very wise thing to do, of course, when you have noisy measurements and you don't want to solve this with equality design. So people normally solve these equations on least square way, just like a Kalman filter. Okay, but there's many variations of how to do it. But conceptually, that's what's going on. Okay, so this is output MPC. You can implement that after some filtering here. So what did Jan Willems, this behavioral guy, have to say about MPC? He said, well, MPC is a little bit brute force. I guess he had a point. That was in 2007. Of course, nowadays MPC is much more developed than back then. But he also said MPC is an area where all aspects of the field come together. He recognized this already in 2007. And I guess now that the theory is much more developed, people have a higher opinion about it. What's interesting nowadays, the MPC people accuse the computer scientists of being brute force. So the story escalates. If you ask an MPC person, maybe I will not reveal the source of the code, and you can guess, he would essentially say, well, you can take a take on elegance, this brute force elegant, but whatever you think, it's the gold standard of control. Cannot be. And that's a statement, it's true. It's the gold standard of control, meaning this is the best thing you can do. If, some assumptions, if you have an LTI system, if it's deterministic, and you know the model. Under these conditions, you cannot beat MPC. It will be just the best thing you can do. What I want to do now is, starting off now and then essentially after the break, is getting rid of these assumptions. How can we now run MPC without a model? And maybe now that you've seen the precursor of that, you can already guess what we'll do. And how can we get away with determinism and linearity? So a small preview before the break. So here's the deep C going from the MPC to the deep PC. It's very simple. We take this, which was previously the model equations, ABCD, that we run forward and backward in time for prediction and estimation. And we replace the model conditions by the fundamental lemma. We say we don't search for U, X, and Y compatible with the model. We search for U and Y in the image of our data matrix. So that's what the fundamental lemma says. We replace this by, we search for U and Y in the image of our data matrix. How does this correctly go? So we have our data matrix. It could be any of the data matrices I showed you, just having independent trajectories, Hankel structure, whatsoever. Let's assume we have the data matrix offline from past data. You could do things as adapt this online and so on, but I'll not do it here. So we get this offline. And we say any trajectory has to live in the image of trajectory matrix. That's a fundamental lemma. In particular, the trajectory when you go backwards in time, and the trajectory when you go forward in time. The backward in time, U, ini, Y, ini, are your latest real-time measurements that you used for estimation. U and Y are your prediction variables. They predict in the future. They have to live in the image of that matrix, meaning they exist the vector G, with this in the image of that matrix. And now you optimize over G, U. So essentially, instead of having here the model for prediction estimation, you just use a fundamental lemma. You've got this non-parametric model for prediction estimation. You can show that this is perfectly equivalent to MPC, equivalent in the sense that these two optimization problems have the same feasible set. And that's the same optimizers. Essentially because they span the same trajectories, as I showed you before. Okay? But of course, this result is only purely academic and idealized. You run in a simulation, it works. You put an epsilon noise simulation, it breaks. So what we need to worry about, maybe after the break, is how do you go from this idealized result that is just using raw data instead of a model to make it, applicable to, nonlinear and stochastic systems. But conceptually, this is it. Just use your fundamental lemma to predict ahead and go back in time for estimation. Maybe now is a good time for questions, and then we'll go into the break. Yes? Yeah. We will do this later on. As you can anticipate already, G will not be a unique solution. And so you can bias the solution by adding some regularization on G. That will help you to robustify it. Yes?
How do you handle if you have a lot of measurements you're trying to get? How do you handle the closing dimensionality?
Got it. So this matrix here, good point. It has m times t rows. No. M times, no, or more. It has more rows. Let's see. This matrix has rows as many as your past data and as many as your future data, which is very much the same dimensionality as the ABCD in the MPC. So the number of rows is the same. But you may have, first of all, a lot of columns here. More data. This is something you can get rid of by just averaging data if you want to. But more importantly, you write down the matrix for MPC. You write this all in a big matrix. This matrix will have a triplet structure. It will be something like a tridiagonal or a diagonal entries. The ABCD repeat themselves, just a recursive element. So this will be a big sparse thing, which MPC solvers heavily exploit. This will be a dense matrix. And that's indeed the price to pay. So the price to pay when you're using raw data is that computation becomes larger. It will not be prohibitive for the problems we look at, but it just becomes larger. So what can you do about it? If you really care, you could, of course, do some pre-processing of that matrix. But if you do pre-processing, you may just well identify more. But people explore different, LQ decomposition. I don't know what pre-process that matrix and make it sparse. But you definitely figured out what's the price to pay. More computation. Are there further questions? Yes. Sure. Correct. So at least in this particular approach, we know we have the notion of a state. And also in other data-driven methods, just say in reinforcement learning, you assume there's a big hidden Markov decision process behind you that explains the world, but you never identify the Markov decision process to learn its states. I fully agree, and thus maybe notions like observers are irrelevant. The strength of that is for any real world problem, the real state space is infinite dimensional anyways, right? If you model things in very, very detail, you can pile up further and further state equations until you go to PDEs, meaning our cute finite state models are anyways approximations of the world. Whereas such approaches, where you never set the state dimension, you can get actually sometimes more precise results. So you don't use the notion of a state, a finite state. But yeah, there is none. Absolutely right. Yes. So here I really, for this constraint, I use my recent most estimation of length T. So just like in the model-based case, length T greater than the lag. Now, for what is in the matrix, I use only offline data, offline. Now, of course, you can think about having a sliding window or forgetting factor, or I don't know, whatever mechanism you want to adapt this online. It turns out people are doing that, but I've not seen anybody having a theory for it. There's at least 10 groups around the world that work on how can you make this thing here adaptive. And there's a lot of simulations, but nobody has a good theory on how to do it. True, yes. You can use this also for fault detection and ask whether the data you observe is compatible with data in the library. Let's say if you have a nonlinear system, maybe you want to forget the past because your linearization here is different from linearization there. And thus you use a sliding window. So it depends on the assumptions you make on your problem. Right. Coffee? I mean, I have coffee all the time, but good. Let's take a break. Good. So our numbers are cut in half now. What happened? The first part was not exciting enough, or they had a business to attend. So for the survivors, the rest, very quick recap, just 2 slides. I want maybe as a recap. One is this fundamental lemma. Point is, if you're interested in characterizing the set of trajectories, as you would do for control, prediction, estimation, you can do this with a model, or as I showed you alternatively, you can equivalently do this just by working with the raw data that would also characterize a set of trajectories, provided the data is sufficiently rich, meaning in particular that matrix has rank m times p plus n. So you need to have at least m times p plus n independent columns. If you have that setup, you can go into, for instance, predictive control, and say normally in predictive control, you have an ABCD model to predict forward. You have an ABCD model to run backwards in time for estimation. This is now what spans your set of trajectories. So the model-based equations, you could just write down these data-driven representation where you say any trajectory of the past and any of the future, and that's essentially one continuous trajectory, has to lie in the image of the data matrix. So there's crystal vector G, that H times G is this trajectory. That's sort of the main core idea about everything. And now what comes afterwards, essentially, how do you make this practical? Because there's a few issues that people already pointed out. One is, of course, this matrix is dense, so a little more computational power needed. But also the fact that this matrix is low rank is never true in practice, because you always got noisy data, nonlinear data. Likewise, this equation essentially says what you're looking for is a linear system. Take linear combinations of trajectories. That's what this does. Take linear combinations of columns. Not every system is not linear. So how do you robustify yourself to all these issues? And this is what I want to discuss now in the second half of this afternoon. How do you make yourself robust here? And when you go to machine learning conferences, they have a philosophical approach to such problems. Say, damn, things don't work. Let me add one more parameter. Let me write a for loop, tune the parameter, see if it works. If it doesn't work, I add another parameter, I write another for loop, and I keep on doing it. So this is what is called regularizations, more or less. Essentially add some extra parameters and tune them until they work. That's, of course, very slippery slope, but you can make it more precise and more rigorous. So what are the regularizations we need to add to the problem? I'll first tell you what the regularizations are in terms of high-level motivation, and then again, we'll go a little bit more into the mathematical details why these work. What are the issues? The first issue is your measurement data, your immediate measurements will be noisy. Just like when you use a model-based approach, a Kalman filter, the output measurement you get is noisy. You don't do any sort of normal ABCD identification or initial condition learning by just solving equations. You solve these equations in the least square way. It's a Kalman filter. And we do the same here. We don't solve this equation of equality sign because likely they will not even be feasible. The equality will not hold true. Instead, what we add here is a slack variable and search for the smallest slack solution. Okay, for instance, make this here something like sigma squared. That means you solve this equation in the least square fashion. Okay? So essentially, this is a moving horizon least square filter, and we penalize the slack variable. Okay? And this is actually fairly exact in terms of this slack variable will take the value 0 if this equation is feasible with equality design, and whenever it's infeasible, we'll take a positive value. So that's sort of a standard trick. I guess anywhere in optimization MPC, you just add some slack and search for the least slack. That works well. But there's a much bigger issue at play here, which is that this matrix here will likely not be full rank, right? Because if your system is not deterministic LTI, there's no hope for this being rank ML n times t plus n. So you need to also regularize, and I guess the answers are given by one of you before. You can still play on the fact that if this matrix, that is typically a long matrix, will have a huge null space. So there are many solutions G. G is how do you combine different columns of that matrix to get your final prediction. It's literally like in the motion primitive case, you can go up like this, sideways like this, and you get this trajectory. But there's not a unique way of doing this necessarily if you have many of these columns. So you can play on the fact that there's many combinations of G you can choose, and you add some sort of regularization on the G. Why is it important? If this matrix has full rank, then anything else lives in the image of the matrix, any of those. It is given any measurements and given any future trajectory, there will be an image of that matrix. So if any U and Y is suddenly feasible, and the optimizer will use that, and take exactly the U and Y that puts the cost to 0. There's nothing adhering to the physics anymore. Right? So that's why you need to constrain which linear trajectories are you allowed to take.
What kind of function?
I'll tell you. There's not a unique one, but I'll give you a few choices. So let me give you a little bit of an insight. One of them is, I guess, you can take a Bayesian interpretation. Bayesian essentially says you can enforce a prior. You have some prior knowledge, and you try to enforce this prior knowledge through this regularization. And in classical estimation, there's actually a one-to-one relation between them. For instance, you can take as a regularizer a one norm G. Would a one norm do? It would promote a sparse solution. So if you put here one norm, G in one norm, it says take a sparse solution G, meaning your G will have many zeros. Many zeros means you take a sparse selection of columns from your trajectory matrix, so only a few of those, which means you construct essentially a low order basis. Essentially, that's your surrogate for this matrix should be of low rank. It's not, but now I just take a sparse combination of columns. We'll make this more precise later, but that's one way you can justify. Another way how regularization is normally justified is through the lens of robustness. Namely, you can also make the argument precise that robustness is equivalent to regularization, which is a classical trick people play in operations research. And if you've never seen it, it's quite an instructive argument. And I want to quickly show you this in mathematics. It's not sophisticated mathematics. All we need is triangle inequality. So if you know Pythagoras, you can derive it. And let's look at a simple problem. Say we want to solve these squares, something like ax minus b. We know the solution, right? X is the pseudo inverse of a times b. Then make the story more interesting. Let's say a is unknown. So we have something like, there's not a, but there's an a plus delta of x minus b. Where delta characterizes the uncertainty. Just like here, this matrix has a lot of uncertainty. Now, what's the way of solving this? What's even the right way of phrasing the problem? So people in OR would tell you, the right way of phrasing this problem is to say, let's not solve for the best solution, let's solve for a min-max solution. Let's find the best solution subject to the worst case uncertainty. So it's something like you maximize all delta, which are less than some constant rho in some norm. So you say, I want to solve this problem robustly. That means I give myself an estimate, uncertain quantification. Delta can be any matrix of radius, of maximum, whatever, norm rho. And now I want to solve this min-max problem. Is it reasonable? Now, how do you go about solving this problem? So you might be inclined, when you see a norm or a sum under norm, there's one trick everybody plays, sum under norm is split up into two norms. It's called triangle inequality. So you say this is less than min-max, and here you have ax minus b plus delta x. Pythagoras, triangle inequality. Further, notice that the triangle inequality here is actually tight. It holds with equality. Why? Well, delta is anything in a norm ball. It can take any direction. Particularly, I can make it so that delta times x and ax minus b are two collinear vectors, and the triangle equality is exact. So this is without loss of generality. And now, a minimize of x, go back to the original colors, a minimize of x, a maximize of all delta less than rho. And inner maximization is trivial, because maximizing delta x, where delta is less than rho, will just be rho times x. Minimize of x, ax minus b, plus rho. And what I've just shown to you is robustifying a problem is equivalent to regularizing the problem. And once you understood that trick, you can do the same trick with now nonlinear functions with different uncertainty sets and whatsoever. It's always the same trick. Keep on bounding the right-hand side and so that it's tight, and then find an easier formulation. But main takeaway of these slides are two things. If you want to robustify, you need to regularize. Or if you want to incorporate prior knowledge, you also need to regularize. So prior knowledge could be that this thing here is low rank, or robustification could be that this thing somehow is something nominal plus an uncertainty term, and both of which can be handled by adding here appropriate regularizers. So that's the high-level perspective. Now let's zoom into what are possible priors and robustifications. So one sort of regularization is, can we incorporate some implicit prior that comes from system identification? In particular, I want to incorporate this low-rank pre-processing idea. Namely, I told you already before, you only look at this part here. The matrix you get will not be of low rank. So before using that matrix for the design, you could do a low-rank pre-processing, because you don't take your original data, but you find the closest match so that this matrix is of low rank. Find the closest low-rank approximation. Once you have that low-rank approximation, you then solve your control problem, data control. Low-rank approximation is hard. There's heuristics. Let's see if we can turn this into regularization. And what I want to show you now is a bunch of cheap tricks, each of which seems to be trivial, obvious, but at the end we'll end up with something non-obvious. So let me go through a sequence of relaxation. Relaxation just means I blow up the feasible set and make it larger and see what we get. The first thing I'll do will not change anything. It's this one. Namely, I do here a low rank approximation, meaning that matrix H of U hat Y hat has low rank. Since this is low rank, there always exists a sparse solution G. So I can always find a G that is constrained in zero norm, so a number of non-zero entries by this. Because the matrix has rank ML plus N. So the G I'm looking for only should have ML plus N non-zero entries. I can add this extra constraint without loss of generality. It will not change anything. So now that matrix of low rank. That didn't change much. Just made it look more ugly. What is really hard is that rank constraint. Nobody likes rank constraints. So let me cross it out. I don't do any more low rank approximation. I don't care about this. I think rank constraints are hard. Non-convex, non-differentiable, everything. I'll just cross it out. That's, if you want convex relaxation, I just blow up the feasible set. Now I have more options. Now there's no more low rank constraint, meaning the closed approximation U hat to UD is just U hat is equal to UD. And say for Y. So the inner problem now is an exact solution. Instead of U hat Y hat, I just take again the raw data. This problem is erased. Here. What have I done? I've just crossed out the things I don't like and now solve a problem over a large feasible set, formally what is called a convex relaxation, but it hopefully becomes easy to solve. Now, zero norms are also not nice. Zero norm says any vector G that has a certain amount of non-zero entries. That's also a combinatorial problem because I need to go through all combinations of zeros and non-zero entries. What's the closest approximation to zero norm that is convex? It's the one norm. It's replaced by the one. So again, a convex relaxation. Now I have a large feasible set, but at least now this is a convex constraint. Next to say I don't like to have the one norm as a constraint. I just add the one norm here as a cost. And if I choose that term sufficiently large, the same as adding as a constraint. So I lift it up here. And what I've just shown to you is I can approximate, auto-approximate, low-rank preprocessing by a one-norm regularization. So in words, what it says, L1 relaxation is a low-rank approximation of this preprocessing. And maybe one thing that's even more important is here in this low-rank approximation, that goes back to the question you had before, I need to choose the order of the system. I need to a priori tell myself the system I'm looking for is order n states. Here, I don't have any more order selection. I never tell myself I look for a system of order n. Instead, what I have to tune this parameter in front of my one norm, this regularization coefficient, right? I need to tune this one, but that's sort of a smooth version of choosing the complexity of the system, choosing the state order. Now I can do this in a more, if you want a smooth way, and I get around the problem of ever figuring out an order of a system. If you just were to run some experiments now on a numerical example and see how does this perform, and I plot performance over this parameter here, where I tune essentially, if you want, so the complexity of the problem, the state dimension, through this regularization coefficient, you would see the following. You look at the realized closed loop cost. Initially, don't do any tuning, you just set this guy to 0. Things don't work very well. But then you start increasing this coefficient. Things go quite nicely, very quickly. You're down at the slow plateau. At some point, when you make this too large, performance goes up again. You over-regularize. And this is sort of the plots you should expect. Now you have a one-dimensional tuning parameter, just like before, the state orders a tuning parameter, and that gets this performance. Now, is that a good or bad thing? Maybe you should look at the axis here. Anywhere between 10 to the -1 and 10 to the 4, I get good performance. So it's not like I need to tune this very, very exactly. Over 5 orders of magnitude, this just works. There's nothing like where you need to run a big for loop and tune this forever. Anything between 10 to the -1 and 10 to the 4 will do a good job. So it's easy to tune this thing. At least for this example, but this is what the plot looks like for every example I've seen. So instead of doing a low-rank preprocessing to identify a system of suitable order, you can just do a one-norm relaxation, which is very easy to tune. And it gets you around the problem of selecting a state dimension. Meaning now you're compatible with any system of any order that has generated the data. Yes.
So this is control cost plus lambda and G1.
This is no. This is, maybe I should clarify. This is a realized closed loop control cost. Only the yellow part. It's not with the lambda times G. The reason why things become cool when you over-regularize, because then you have a very high cost on G, and then you're selecting more or less G is equal to 0. And then you get a full control cost. This is something you have to find out. The way we do it is really we just search over a log scale, lambda from, I don't know, 10 to the minus 5 to 10 to the 5. Give me 10 options, and then typically very quickly figure out this plateau.
But there is still different. So it's scale up that removes parameters from G's. The impact of those parameters is smaller as it grows.
Yes.
Up to a point.
Right, yeah. Also, it will choose different values of G whenever you call the optimization. I can do this in the receding horizon, you get new measurements, you call the optimization. This he will take different non-zero entries then the next time, and so on. All right. So take away adding a one-norm regularizer already solves your problems, or part of your problems. It will essentially do for you the low-rank preprocessing, at least a surrogate of that. And very efficiently so. There's another regularizer I want to present to you, which is more along the lines of what people normally call cert equivalence. That goes as follows. So let's split this slide into two here. So maybe I put here the ARX representation of the predictor, if you had a model. And here I put the deep sea representation of the predictor. So in the ARX way, we had this equation as we put it: y is the observability matrix up to length t times x ini plus your impulse response matrix times u, where x ini satisfies a similar equation. You get it by just running this equation backward in time. So you have some y ini is the observability matrix up to some initial horizon t ini x ini plus your impulse response matrix. Okay, this is the equation that I've derived for you. Or maybe let's quickly jump back that we're all still on the same page. It was here when I told you I can write the solution to an ABCD question like this. That's the normal way you write it, or I can write it in vector matrix form. We have here my y time series, I have my observability matrix times x ini, I have my impulse response matrix times u. That's normally how you write things up, also in an MPC context. And this would be the normal model-based version of the predictor. Just this one. So that's the one. And the x ini you get again by running this equation, but just where y and u are taken from past data. So y and u. On the deep sea side, you do things differently. You say that your vector of past data, u ini, y ini, and your future u and y have to live in the image of your trajectory matrix. So in this case, there's your trajectory matrix times g. What people normally do, they partition this trajectory matrix. That is, they write this normally as a partition again into 4 block matrices to be compatible with the right-hand side. So they say it exists a UP, a YP, a U future, a Y future, UFY times G. So this is just a partition compatible in terms of dimension. Okay, so if you open up any paper on subspace methods or whatever, you always see this language UP, YP, UF, YF. It's just essentially take your data matrix, partition it accordingly so that you have blocks of similar size to it. Okay, and now what I'd like to show you is, can we figure out a regularize on the G to one-to-one get this? That would promote as if we were essentially some sort of least square model application. So we get the same solution as the model would give us. Okay, so how do we go about this? So here you see your y is related in a linear fashion to u and linear to x ini, where x ini you can again linearly derive from y ini and u ini. And you can work out the details, will have some O inverse and so on. Not so important what the formula looks like. But one thing I can definitely say is y is a matrix K times u ini, y ini, and u. Where the matrix K you would get by, I guess, inverting this to get the x ini, plug it in here, and then you get this. So there's explicitly a model-based predictor that would have these properties. So you could say, well, I can learn this from model, or I just learn the K from data. So if you learn K from data, it looks as follows. You would just do a least squares, where K is learned from data. You would say K is your argument, minimize some least square criterion, where you put here essentially the data you've seen in between. So you would take your output data here and your input data. You would have here YF minus K, EF, UP, YP. So you take your data, partition it is here, and then you want to find the K that minimizes the least square error. So you have on the left-hand side your Y data, on the right-hand side you have your U data, both past and future, as you partitioned here, and also past Y data, and you find the K. Solution of which is just given by the pseudo inverse. So this would be something like YF and pseudo inverse of UP, YP. And then what you get is your final predictor in closed form, which is Y is this here times that, which is YF, UP, YP, F. Pseudo inverse times the real measurements, by in the future. And this is the formula you ultimately implement for your predictor. This guy actually has a name. It is called SPC, subspace predictive control. Again, some people invented in the 90s, and apparently is used all over the process control industry, as I was told. I don't work in process control, so I cannot really validate that statement, but at least people tell me if you work with batch reactors and chemical plants, apparently this is what you use for your models, and then you run predictive control on that equation. Apparently, but it was from a well-informed source. Let's take this as fact. So this would be the predictor as you get it in a model-based fashion. That doesn't look all that different from our deep sea predictor. Looks fairly similar. Let me make them look a little more similar. I could write this as here. I can write this as y is equal to, create some space here. It's equal to the last equation, which is yf times g. Where g solves the following. Namely, I have the other equations here, u ini, y ini u is g. Sorry. U ini y ini is u is equal to up yp uf. Essentially what I did, I just took the last equation, which is this one, and these are the first three equations. Now this here looks surprisingly similar, especially if I would take here solution G to be the pseudo-inverse, I more or less would get the same formula, as you can see, right? In general, I could always write this as y is I take a particular solution of these equations, namely the pseudo-inverse solution. I have here my yf, up, yp, f to the inverse times u in y in u plus a yf times G homogeneous. The G homogeneous is in the null space of that matrix. Okay, so any solution to my deep C equations I can write like this, without loss of generality. And if I care about recreating the model-based equation, then I should just take a G which is a minimum norm in the null space. Okay. The takeaway is to recreate, if that is desirable, to recreate the model-based solution, we need to penalize the null space. We need to penalize any homogeneous solution, which gives you another way of regularizing. Now you penalize anything that is in the null space. That might be another regularizer. And then you would get the same solution as you could have figured out essentially by some sort of least square identification of your data. If you think that's a good thing. So this is what we call a certain equivalence regularizer, because you get the same solution as just doing least squares. Let me quickly show you this nicely typed up in LaTeX font. So that's the same argument. So you know that if you do an indirect cis-ideal control, you would get the following. You would say there's a linear relation with y, u in y in u, where this matrix that relates them is found by a least squares problem. The data in least square problem is just your data that you collected, suitably partitioned in 4 blocks, be compatible with y, u in y in u, which gives you this multi-step SPC predictor, which is this. I could have just derived for you. And if you want to recreate that in the deep C, you can choose a regularizer that exactly recreates it. And again, that's the same I just showed you, just now typed up in form. Namely, what you do here, you add a regularizer that would do a certain projection, and it would do a projection on the null space of this matrix. So you project orthogonal to the kernel of that matrix. So you penalize anything as null space, and it turns out the solution you get here, choosing this coefficient here sufficiently large that this is really penalizing the null space, you get the same as here, as the model-based setting. So in this case, again, it's regularization incorporates a prior. Prior is there's an LTI system behind it, and you can enforce that by a particular projection-based regularization. How would this work? So here's a stochastic LTI system. I forgot actually how we created it. We again look at some sort of realized closed loop cost. So here we look at a percentage error with respect to the best deterministic model-based solution in the control cost. If we were to do any sort of one norm regularization or a more general p-norm regularization, I get these trade-off curves with the plateau down here, and you over-regularize. So this is what these curves always look like. Here, I know there's a stochastic LTI system behind it. So it may make sense to actually identify an LTI system. And if you use my projection-based regularizer, cost goes down and it stays down forever. Meaning you don't need to identify anymore this plateau. You just need to identify only a value that's sufficiently large. Because you know there's a LTI system behind, so you cannot over-regularize. That effect will not happen. Okay, so if you already have the idea there's some LTIs behind, then doing this particular organization does good things. It turns out you don't even have to search for this value numerically. there's people in statistics that have clever heuristics that allow you to compute the regularizer beforehand before running any experiments or do cross-validation or whatsoever. In particular, something called a Hanke-Rouse heuristic that tells you a priori, without you ever running any experiment or validation or whatsoever, what this value should be. So this can be done offline a priori. So you can actually find the exact best regularizer. Okay, I just heard somebody yawning and breathing. Let's quick take a step back. What I just did for you was to make these arguments here a little bit more rigorous, where I told you regularization serves two purposes. One is incorporating priors, the other one is robustification. I just showed you two ways how and why you can incorporate priors, how you can choose these regularizers to incorporate priors. One was a one-norm regularization to incorporate the low-rank preprocessing. The other one is the idea, maybe there's a stochastic LTI system behind it that you can identify using least squares, and there's also a regularizer that does for the least squares identification implicitly. And those are the two I just derived for you. Next step, I would have a few case studies to show you how does this work on a real system, on a complicated system. Before we go into the case studies, questions on the derivation of these regularizers. Means either everything is crystal clear or we're all tired. Let's move on with the assumption that it's clear. You had something.
Can you please go back to the views?
The handwritten one?
The fellow projection is unclear.
The projection?
Yeah, that is the one we showed for this class.
Ah, okay. So the idea is, assuming a ground truth system would be of LTI. You observe that, but you observe that data maybe with some noise. There might be plus noise. And so what any sort of statistical maximum likelihood argument will tell you, the best way to find the K if you observe noisy data is to solve the least square problem, the minimum to the left and the right hand side, which is what this is doing. That is the best thing. And it turns out this is equivalent to taking a deep C problem whose solution you can write as this part, which coincide with the least square problem, plus some other part, and that other part you just put as a penalty in the cost. Is that the question? More or less.
This is the value put in the after post in the MPC.
Correct. So in the MPC, you now put here something that would penalize the null space of this matrix. So I only now search for solutions G, which are which is zero. So for solutions G, which are orthogonal to the null space.
So this part I will. I mean, and then this describes the blue. If I remember correctly, color. Part of
this would be the red one.
Yeah.
The red one would be this: I project orthogonal to the null space, because I know what is behind the data is it's an LTI system. And it turns out this is then the best regularizer to choose. And it turns out I cannot over-regularize. This thing will never go up. It will always be down there. I just need to take a value sufficiently large to make sure everything in the null space is really less than zero. Whereas other regularizers would have this problem of you can actually over-regularize. Like the blue one. Like that would be, for instance, the one norm case. Yes, in the back. Yes. We'll get at that. It was backwards in time. So we observed numerically one norm regularizers were working well. And then we thought, well, do they do anything useful? And then we were going essentially through all this manipulation backwards in time. So I thought, well, we know this should do intuitive something similar to a low rank. So what's a path that gets us from low rank to L1 regularization or vice versa? So we knew that we had the intuition it must be their connection. Then we derived this process essentially going all these steps backwards. Correct. The way I tell it, the story is now the inverse way we discovered it. let's put this into practice. So here's a case study. We took a wind turbine model from General Electric, GE. The model is the following. You model the mechanics of the wind generator. You model the power electronics, filters of the measurements, the way the power electronics are controlled. There's like, control for the outer loops. Says you should provide some frequency response. There's an inner loop, how you control the current. And there's some nonlinearities in power electronics, which are these blocks, which is a phase lock loop, meaning from voltage data, AC voltage, you extract the frequency measurement. And this is a coordinate transformation between normal coordinates and rotating coordinates. Okay, so these are the main nonlinearities of the model. So that's a detailed model, it has about 37 states. It's quite nonlinear, especially because of this transform between coordinates. That's the polar coordinate transformation. In this outer loops, there's other things going on, like maximum power point tracking and similar things that also add nonlinearities. Now, what you observe is the following. Say if the transmission line connecting the wind turbine to the grid is long, the connection is weak, then any sort of small fault on the grid may trigger oscillations in your power across that line. So that's active power P, reactive power Q, and these can be easily oscillatory, especially if that line is long. Now, if you're the poor guy commissioning the controls for the wind turbine, say you don't have a grid model, nobody has the grid model. On top of that, if you're the guy who does that, you're typically either just from the distribution network operator or from the wind farm company or from the company that manufactured these power electronic loops. But typically all of this is unknown to you. So the grid is unknown, and typically all of this here is also in practice. So the way these things are damped in practice, they close here controller between the measurements, and then they feed this into the current controls, and typically add here a bunch of single input, single output filters that they tune until these oscillations are stabilized. It's actually a quite good case study to apply any data-driven control. Because in practice, simply this cannot be solved in a model-based setting. So here's what happens when you run the deep sea. So you observe the oscillation data, say here in total for like a total of 2 seconds. What I show you here is the active power and reactive power. You here collect data for a total 2.5 seconds. This is the data from which you build the data matrices. If you were now not to do anything, what would happen are these grayish curves. You see the grayish curves are growing oscillations, and they're not only unstable, but they're also nonlinear, which you can see by the shape of these oscillations that are very zigzaggy. So that doesn't work. If you now run the deep sea with any of the regularizers you can imagine, like a 2 norm squared, which is the easiest one because you can solve it in closed form, 1 norm, or the projection-based regularizers, all of those would actually very quickly dampen this oscillation in a complete black box setting. Okay, very nicely. If you look at a trade-off plot, so you plot the closed loop control cost, the realized one, over your regularization coefficient that you add here. For the 3 different regularizers, you first see they all have this nice plateau shape, and before they go up again, you can identify for all of them a priori already the minimizer. You don't need to run any for loop. And apparently the wind turbine is sufficiently linear that the certain equivalence regularizer performs quite well, meaning things go down here and stay down. Okay, so you can very efficiently learn this thing, and it works really well. So that's encouraging. That's now a 37th order model. It works well. We're very happy with it. And then you can make it always more complicated. Okay, so let's take a case study plus. Now let's add a full-blown wind farm in the grid. Now we have 10 of these wind turbines. Okay, so 10 times this thing. So that already gives you 370 nonlinear state space models. I connected to a grid. I took an IEEE 9 bus system, a classical system from benchmark literature. It has 3 synchronous machines here. And I model all the machines and everything. So now we had a couple hundred states almost. And now I want to provide fast frequency response, meaning there's a fault in the grid. There's I forgot what it simulated, but typically some load steps or closing the opening and closing of a line. And the wind farm should provide some sort of frequency support. That is, frequency will drop after a fault, and they have to inject active power to stabilize the frequency. So here's what happens. What I give you here is the frequency. I think measured one of these generators. We got which one. And I show you the control input by the wind turbines. So what happens, you have a fault. After the fault, frequency drops. And you have to inject active power to support the frequency. Now, of course, the generators by themselves also have controls installed that should stabilize that fault, and they will. So if you don't do anything, this will be the response curve. Sort of the classic hook curve in power systems. Open up any power system book, page number 1, you will see this picture. So if you don't do anything, this will be eventually stabilized. Now, if you run some sort of identification and control, turns out identification in this case doesn't work well. You will get this curve, so things would actually go way downhill. Maybe recover after a while because the generators pull things back up, but here the lights have turned off. So as you can see, the simulation, the baseline frequency is 60 Hertz, some American system, but typically at this point here, everything's already broken. If you add now the deep sea with any regularizer you can fancy up, like a 1 norm or 2 norm squared or projection-based 2 norm squared, it would actually quite nicely arrest the fault and things would stabilize very quickly again with all of them quite nicely. Now we have a really complicated large-scale system. If you look into what the data control doing, it does something very interesting. It's the same what a human operator would do. And the question is, where the hell do you get the active power from to stabilize the grid? What's the source of active power for the wind turbines? Well, it's the rotational inertia. That your blades are spinning. You can suck kinetic energy out of the blades and push it into the grid. And that's what it's doing. These data controls take energy out of the rotor speed is dropping, and push the active power into the grid. Which, that's what a human operator would do as well. It's quite clever, but we never told the algorithm to figure this out. It's so by itself, which was quite nice to see that confirmed that it could do these things. So takeaway, these things work really well on rather complicated models, which was, of course, encouraging to see. Good. Further, this thing is very easy to implement. I have here a link to some of the code we use for our bachelor course. So it's literally just this one, quadratic optimization problem, and play with it after as you want. So that's why people also like it and adopt it, because it's that easy to use. Yes. That's a simulation, yes. No, that's not hard-coded. I have some also real-world data plots for power voltaics converters, but I'm not allowed to share them. But it works. I never got to play for real wind turbine, unfortunately. If you have one, I would love to play with it. So, all of this was essentially linear, right? Because in the back of the hood, what we do, we take linear combinations of trajectories you've seen. There's no reason why the hell it should work for a nonlinear system. But all the case studies I showed you work for nonlinear systems, right? So how can we make sense of that? And there's different ways you can do it. Maybe let's first discuss sort of the ways most people explore it. So let's take any of our deep sea formulations. Oh, where's one? Let's take the fundamental lemma here, for instance. So what is really behind everything is to say, I take linear combinations of trajectories I've seen, and I get new trajectories. Makes sense, superposition principle for a linear system. Not true for a nonlinear system. What could you do? In general, when you go from linear to nonlinear, there's always two things people do. One of the tricks you play. The first trick you play is, maybe it's not linear in original coordinates, but it becomes linear in feature space. Meaning if I wrap some nonlinearities around it, maybe things become linear. That is, maybe the problem is not linear in u and y, but maybe it's linear in u squared, y squared, u cubed, y to the power 3. I don't know any of that, right? So what you could do is just take your data and fit it through a nonlinear dictionary of functions and hope that things become linear in that new dictionary. That's actually a mathematical theorem. It's true. You can always find a change of coordinates so that things become linear in the other coordinates, right? So there's things like Koopman operators that exploit this, dynamic mode decomposition, and so on. The problem is, to do that, you need first of all to find this nonlinear transformation. It's typically not like a bijective transformation, but you always need to go up to a very high dimensional space. Meaning I can replace my data, of course, by polynomials of the data. Price to pay is that this matrix explodes by size. Conceptually, it works. Price to pay, of course, is computation increases for it. And there's many algorithms out there that do this thing, like most famously a thing called Cindy, but more or less what it does is taking nonlinear features of the data. I don't want to do that. I want to choose the route number 2, which is also some sort of without loss of generality route. And it goes as follows. Another theorem, every system is linear. True. It's a fact. I can embed any nonlinear system under certain assumption, weak assumption like analyticity or so, into a high-dimensional, infinite-dimensional linear system. And again, there's methods to do this, like Kaleman, Volterra series, and so on. The pragmatic engineering intuition is everything on a finite time span can be approximated by high-order linear time invariant system. But give me any time series, I can approximate it arbitrarily well if I choose a high enough state order. Again, price to pay is, to do this, you would have to go to very large, in theory, infinite dimensional system, state space representations. But you can go that way. The other question? Because you just raised your arm?
No.
All right. So these are sort of the two principal ways. Either you go through nonlinear basis functions or you go to high dimensions. I find that going to high dimension works better. And so what we do is just pragmatic, like let's take data as much as we can handle within the sampling time of our computation, because in the reality you need to, whatever, every 10 milliseconds pump out an optimization solution to your problem and see how big of a problem you can solve in that time frame. So you have a high dimensional object behind and let the regularization figure out what are the relevant essentially features in that data set. And again, if you want to make a theorem, you can make that theorem saying, yes, everything is linear in infinite dimensions. But in practice, you, of course, you choose to truncate to something useful. I had a little video for you. Let's see this one. So this is the first experiment we ever ran. That was in 2019, where we just applied this thing to a quadcopter. We were first manually flying the quadcopter by hand flying, then got us the data matrix, checked the matrix. Now we had our data matrix, and then we told it, please fly figure 8 circle. We would do this very well, and also with deep inclinations, with a lot of sine and cosine nonlinearities, and then it would do rather well. But of course being by no means linear. The idea of just collecting a lot of data, adding regularizers would work rather well. But then that was in 2019 or 2018, and it took us like 4 or 5 years to figure out a theory why that works. But now we figured out multiple, but let me just tell you one. It turns out many people have thrown this on many things. It seems like these days a favorite exercise for professors to tell their master students, please implement this on XYZ. So here's a bunch of examples. So we have many implementations on grid-connected converters, synchronous motors. We have it in all buildings in Zurich that we have under control. Power oscillation damping, at least simulations, battery charging, wind turbine control, combined cycle power plants. There's many of those. People in robotics have also applied this on many case studies. My most favorite one is the digging the dirt. So we had a robotic excavator, 12 tons, and we're digging dirt automatically with deep sea. That was rather fun. But the most creative one was greenhouse automation. So in the Netherlands, they had a tomato growing competition, like an AI competition, which AI algorithms can grow the biggest and fattest tomatoes. And apparently the winning team, as I learned later, also used the deep sea. I'm not sure how to interpret that, but apparently tomatoes are sufficiently linear that you can apply them that way. Long story short, why do I show you this? Because all of these case studies are nonlinear, and it seems to work across all of them very well. And I want to offer to you some sort of principled, or a little more principled justification why it works. And that goes back to this idea that we are not nonlinear. The method at its core is a linear method. It's linear and robustified because regularization is equivalent to robustification, meaning you're not solving the nonlinear problem, but you're robust to the nonlinearities. And robust in a way that model-based control cannot be robust against. And I already showed you one derivation, why regularization is equivalent to robustification. Now I want to show you another one, which is the one that we actually use. And it's called distribution robustification. And now I'm asking a lot from you because, you're set through a few hours here. It's late in the afternoon. So I'll show you one slide or 2 slides of a little bit more probability theory that I'll go slowly. But it's sort of, if you really want to get in details, that's where there's pages and pages and pages of proofs. But I'll try to keep it on a very simple level. So on an abstract problem dimension, what we're solving is the following. We solve an optimization problem, minimize over x, some cost function c of x. But the problem we're solving also depends on measured data, psi hat measurements. Let me rewrite this optimization problem in a more probabilistic fashion that makes it look very complicated, but then you can see what's going wrong. I could also think about this as follows. Instead of taking psi hat as data samples, I could say psi is just a random variable, and I get samples from that random variable. The problem I'm solving is a stochastic optimization problem with a psi sampled from probability distribution, the so-called empirical distribution, that will put a delta at every sample. So you have your probability distribution, like this. You have your samples, psi 1, psi 2, 3. And then you have a delta psi 1, delta psi 2, and delta psi 3. That's a probability distribution. If I sample from that, I get my samples. So just another way of writing this problem is I minimize a random decision-making problem where psi sampled from the sample distribution. Okay, so let me solve that problem. That's the problem actually I'm solving in the back. That's the problem I'm solving all the time. So I solve the problem, the solution to the above problem. This is also called the sample average problem, because that probability distribution is just a sample distribution. So it's called the sample average solution. I plug the solution into my system. Look at this. Devils and details. Here, the problem I'm solving, I have the samples. The real problem follows some other distribution. I have samples from my world, model of the world, my whatever is going on. But the real problem is following some sort of stochastic process that I have no idea what it's about. This is the famous, machine learning people call it the out-of-sample performance or distribution shift problem. It has many names. But bottom line is your samples are only a poor characterization of what's going on in reality. And you'll always suffer this out-of-sample loss. And so that tells you what you should robustify yourself against. You should robustify yourself against only having samples, but not access to the real distribution. Proper mathematical way of stating this would be following. It's called distributional robustification. You want to account for all stochastic processes that could have generated the data. All. Linear, nonlinear, stationary, non-stationary, Gaussian, non-Gaussian. That would be the right way of dealing with it, right? You want to be robust in the set of all stochastic processes that could have generated data. So you're robust modest to nonlinearity. So how do you put this into equations? There's an entire literature about distributional robustness, which goes back to optimal transport and so on. Details are not so important, but it's very, very active. It got like a bunch of Fields medals in the last years in mathematics, and also has transitioned a lot into machine learning. It would go as follows. So you find the best decision, so that's the min over x, and you have your control problem that depends on a random variable. I don't take the random variable from the samples, like here. I say the random variable is from a distribution Q, and I don't know the Q. So I maximize over Q. So this is this part where I say, I want to account for all stochastic processes that could have generated data. That's this part. So I take a max of all distributions Q that could have generated data. Now what is in it? So notice I write here in soup. That's just pedantic, because min and max are not guaranteed to be achieved, but think about it, min max. What is this saying here? So I maximize over all Q, which are quotation marks epsilon close to my samples yeah. Now, epsilon is for you to choose. You choose how close you want to be. Choose epsilon large, you're robust to everything. Choose epsilon small, you're only robust to samples. Now, what do I mean by epsilon close? How can you be epsilon close to samples? But this you need to find some notion of distance in the space of probability distributions. And again, you can pull from the books, there's many of them. The one that works best is what is called optimal transport or Wasserstein metric. So B epsilon P will be a ball sampled at your centered at a sample distribution, radius epsilon. How do you construct the ball? Maybe look at the picture and not at the formula. So you have, what's the distance between two distributions? Say, what's the distance between distribution P and this sort of sample distribution P hat? One way to construct the distance is called Wasserstein or Monchkin-Horowitz or Earth-Move distance. Earth-Move has the most intuitive name. You really ask how much work does it take to shuffle that dirt pile over into that dirt pile. So what you do, you take a psi from here, you compare it to a psi hat from there. So you take psi minus psi hat in some norm, some p norm, and then you measure the expected amount of work. So you integrate this over the joint distribution pile. That's a way to construct a distance. And this being less than epsilon gives you all psi, which are epsilon close to psi hat. Again, hard part of that is there's many joint distributions you can construct that would have the right marginals when you project them here or there. And so you take the inf of all. No need to process details, but it's just like that's the way we measure distance in probability distributions. Now, if you want to solve that problem, you have here an inf, you have a soup of an infinite dimensional probability space, you have an inf of an infinite dimensional probability space. So it's already doubly infinite dimensional. Probability space is not convex, not even differentiable. So it's a hard problem. But it turns out you can solve this one actually in closed form. Yes. So Q is epsilon close to your empirical distribution. And to make these integrals well defined, so that these integrals don't exist in interval of finite variance. But it's all Q of finite variance epsilon close to samples. So if you didn't parse all these details, it's fine. It's just that's a way in probabilistic language to say all epsilon nearby stochastic processes that could have generated data. Now, luckily, some people in math and operations research solve these problems. It's not up to us to solve them. In particular, there's a person called Daniel Kuhn, who spent the last 10 years, solving these type of problems. And it turns out the solution is actually something we already knew. The solution is the following. Distribution robustification is equivalent to regularization. Particularly, you want to solve this inf soup problem, this distribution robust control problem. The solution is the following. That's the same as solving your nominal sample average problem. The one we always solve, we just take the data as it is, and take the data at face value, plus a regularizer. And the regularizer consists of two parts. There's, first of all, there's some sort of weird norm here. And what is in front of the regularizer, the constant, depends on epsilon, that is how robust you want to be, and on the Lipschitz function, Lipschitz constant of the cost function. Okay, so putting a large epsilon means you want to be more robust. Now, what is this dual norm? Sorry, what is this here, this P star? It's a dual norm. So if you select as your probability distance here, like the one norm, then you regularize with infinity norm. If you select the infinity norm, you regularize with the one norm. So for example, if you want to be L infinity norm robust in the space of trajectories, you need to L1 regularize. So you can, again, that's the same results as before, but now with different interpretation. L1 regularization is equivalent to L infinity norm robustness to all nearby trajectories that could have been generated from the data. And when you see these trade-off plots where you say, I plot the cost of my regularization coefficient, you should have in mind that this regularization coefficient, what it really is, it's the robustness radius. So you want to be robust in a radius epsilon, choose here epsilon. Initially you're not robust at all, you get a high cost, then you're robust, things work well, and here you become robust to everything and things break. Takeaway, if you regularize, you become robust in this distributional sense, and that's why also you're robust to nonlinearity. Actually, I would not know, I have no idea, nobody has an idea how to apply such, distribution robustness tricks in a model-based setting. Open problem, but they work really well in a data-driven context. So it's another way of deriving regularizers, but now with different interpretation. Okay, there's more you can say, and I said the theory behind that would easily fill like a full week or so of derivations, which we'll not do. Plus, I don't think I could do them anyways, often, to be honest. So let's not do this. It turns out you can actually quantify that epsilon also from data, if you care about that. So people worked out sampling complexity result tells you, assuming you have that many data samples, you can reverse calculate on a good epsilon. Okay, so people developed such results, such sample complexity. Here with an example, but I'll not show you this. It turns out these ideas you can apply to many more complicated uncertainty sets, not just to epsilon norm balls, but to other uncertainty sets, and to get regularizations. So just to show you, plot here the realized cost in histogram, and I compare it to have a structured or unstructured uncertainty set. The more structure you put in, the lower cost you get. Just put an unstructured uncertainty set, like just a norm ball. Things also work, but you can better worse performance. Not going into the details, just you can do this all. You can apply everything also to constraints. So you want to have probabilistic constraints or distribution robust probabilistic constraints. If you know what that is, good for you. If you don't know it, you don't need to understand it. There's something like a C-bar constraint where you say, I want to be robust in probability up to a certain tail to violating a constraint. You can also make a distribution robustification. So you put a super-walled probability distribution, which will again be something like a regularization. Can be done. So there's many ingredients and extensions you can work out. But given the time, I'm mindful and will not go into that. Questions on this? Yes.
So everything here is to add more stuff to the DPC. There's things that we're not accounting that are not.
Correct.
But what happens is you want to have a representation of things that we know are non-linear. Now that you call it for them, or combine that.
Sure. So you have the idea of, so there's two ways I know how to do it. One is called essentially gray box modeling. So part of your constraints you model as deep sea, part of your constraints are explicit, if you have that insight. That's one way of doing it. The other one is linear parameter varying systems. Familiar with that system class? Meaning you say everything is linear, but parameterized by a variable parameter, which could be a nonlinearity that you know explicitly. And then if you can measure that nonlinearity, you can do everything linear in this context. These are the two ways I know how to do it. But I should be honest, at the core, it is a linear method. It works very well for weakly nonlinear systems. But if you want like the quadcopter fly backflip, let's say you want to swing up a pendulum, you can do this, say, with LPV methods. Yes. What do you mean generate data from a nonlinear model? I mean, all the examples I showed you, the data came from ground truth nonlinear systems. I mean, real world nonlinear systems.
Yeah.
On the real plan. I'm sure people have done it just because the sheer amount of people that tried it out. But I cannot really tell you the results, to be honest. Mm-hmm. Yeah. maybe also that goes to the question, when would you ever apply these methods? You probably would not apply it to an open loop, unstable, nonlinear system, right? You probably want a system that is somewhat already either naturally stable or pre-stabilized through some sort of PI control somebody figured out, and then you would wrap this thing around. But if you have like an open loop, unstable system that is even nonlinear, good luck. You know, nuclear fusion problem or so. Probably would not work. There was a question in the chat. Could you compute deep C with reason methods on Q-learning with performance guarantees? You could. So what you can do, so Q-learning essentially is dynamic programming, a version of dynamic programming where your ABCD matrices are unknown and you search for the value function, in this case for the Q function. And instead of using the ABCD, you could approximate the ABCD just by raw data and then do Q-learning on that. I've seen people doing that. I've not done it myself. So I don't know exactly what the guarantees are, to be honest. Any other question?
I'm trying to get the intuition behind what. So if I have a nonlinear system and I try to look at this trajectory. This trajectory will depend a lot on the place in space I am. So yes, there is a description behind it, but I understand if I'm in specific space, I could perhaps use some higher order model and describe this. And at least the intuition I get is that this epsilon essentially creates a set of higher order spaces, and then we robustify the.
I would say almost it creates a set of possible models compatible with the data.
So, but however,
I need to stabilize in all models within that epsilon ball.
Yes, and I agree, and I understand the importance of the approach on these aspects. But going to the first part, is like the trajectories also depend. So where you get the data from, depend on where you are in the space from the beginning, right? So there should be a case where this doesn't.
Yeah.
So what?
Here. So for the pendulum, it's a good case where it doesn't work. So think of the simplest model pendulum. It's like mass times rate of change of frequency is minus the sine of the angle. Linearization has a negative sign here, positive sign there. So if you would just take a linear model from here, it would be very shitty up there and vice versa. So if the way people got it to work for pendulum or similar problems like that, essentially take linearizations at different points and interpolate between them. So you have one where the pendulum's hanging down, one where it's flat, and one where it's upright, and then you interpolate between them. So you use essentially 3 different data sets, similar to a linear parameter varying system, and then figure out a clever interpolation. Which shows you already the limitation of these methods. Because you can put everything in one system or one set of systems in an epsilon ball, and you then stabilize all. But for the pendulum, this is nearly impossible. So they just did a more adaptive version of that. Okay, 3 different data sets.
The next question is that, okay, I understand if you can split the space into a number of partitions, I understand this would work, but then the next question is how you can do this.
Prior knowledge, yes. Just need to know it, right? If you don't know anything, then there's not much you can do. And those are important questions because obviously there's not one method that solves all your problems, and you can point out the limitations of the method. So it works well for weakly nonlinear systems. If you have more strongly nonlinear and you want to do data control, you need to have prior knowledge and play all these tricks.
Did you consider like having a test? But because essentially, again, you have a space that describes your data. So it's like an anomaly on your data if you have data. So this could result in saying, now I don't trust my model because I have essentially left the space which describes it. I don't know if this is something.
I have not yet. But that's the problem. Say now my data is so far away from my model, I need to do something. By the way, when are we finishing here? So I can finish anytime. I can finish now or.
We have until 6, but it's up to you. I mean, if you think that you are starting something new, you should purchase it.
Sure. How about this? I'll leave you a cliffhanger so that you come back tomorrow. So where's the cliffhanger? Here. You know the saying, the white elephant in the room? There's something in the middle of the room that should be obvious to everybody, but nobody talks about it. What's the white elephant here? What is the obvious question that we didn't ask about? How does any of that perform against model-based control? Because that's the obvious benchmark. Surprise. Every single experiment, you always beat model-based control, no exception. Why? Well, let's finish then.
Sure.
Really enjoyed that talk.
Thank you.
And happy that I could follow.
Very good. Should I turn off the screen?
There is a question.
Ah.
From
Oh, I already answered that one.